Okay, so PS2 is out, and you do Thursday or Friday, depending if you want to use a late day or not. Any questions about that or anything else? Okay. Last time at the end, we were talking about call by reference. So I want to finish up with that before we move on to something else. Just to remind you, there are two kinds of parameter passing in C#. There's call by value, which is what you're used to, and there's call by reference, which is different. And this method call right here, where we're calling try parse with two parameters, actually illustrates both. This first parameter is passed by value, and the second parameter is passed by reference. Now, when you use call by value, the parameter itself, the actual parameter, such as this string right here, can be any expression of the right type. So it could be a variable, which is an expression, a literal, like 45 in quotes. It could be the result of a method call. It could be lots of things. So in call by value, you have an expression, which is the actual parameter, and it's evaluated, and its value is passed as the parameter. How is call by reference different? Such as right here. How is that different from what you're used to? Yeah?
Well, if it has an out there, it passes the reference to that variable, and it doesn't actually have the access to use the variable, but it can store a value into that variable.
Okay. So in call by reference, what is passed is not the value of this variable. What is passed is not the value of an expression. What is passed is a reference to a place where a value can be stored. So you can put any expression here. If you're doing call by value, any expression of the right type. Call by reference, the parameter must be something like a variable, an array location, a place you can do an assignment. And that's call by reference. And whatever value, in this form of call by reference, without parameter, whatever value this variable has doesn't matter. It's the job of the method being called to store a result in this value, in this parameter before it returns. So what it gets is literally a reference back to that variable. Yeah?
You have to, here you didn't declare what type of variable is looping.
Well, okay.
Required at all times, because sometimes it does ask for that.
Okay, so he's saying I didn't declare what type. The reason is this is not, I'm not declaring the method here. This is where I'm calling the method. In the int class, the int32 class, this is where this method would be declared, and it would be a type. It would say the second parameter is an out parameter, which is an int, or yeah, an int. Just like this would be declared as a string at the point of where it's defined. Okay, so that's the fundamental difference. You pass different things. Call by value, you're passing the value expression. Call by reference, you're passing a reference to a variable location. Now, what's the difference between an out parameter? Here's two more out parameters. Or a ref parameter, such as right here, or right there. What's the difference between an out parameter and a ref parameter? Both are examples of call by reference. They're just a slight difference between them. Yeah?
In the reference, you can change, you can mutate it, you can store a value.
Okay, so he's saying that with ref parameters, the method we're calling can store into A and store into B. But actually, that's true of out parameters as well. If these were out parameters, the method would be able to store into A and store into B. Yeah?
Are we assuming that the references are actually already set to be a value?
Okay, so to summarize, he said, are we assuming that the A and B already have values? And in fact, that's true. With call by reference, A and B must have values, and the method we're calling can access those values. Without parameters, you can't pass information in. The value of an out parameter, the value of the variable when you pass an out parameter, is immaterial. It's just the job of the method to change it. So it just depends on whether the information is flowing two ways or one way. Two ways is ref, one way is out. Okay? So I want to show you how this works when a program runs, but I want to see if there are any questions I could answer about this first, about what it looks like in C#. You'll notice that up here I'm passing a sub 0 and a sub 1, a reference to a place in those arrays where something can be stored. Here I'm passing a reference to two variables. Either way, the value stored in the two spots is swapped by this method. Something you can't do. You can't do something like this in Java, for example. Okay? And I will say, here is where solve quadratic is declared. And you can see I do give types there. I say that x1 is an out double, x2 is an out double, and so on. Okay, what we have here is sort of a standard stack heap memory diagram of a running program. And I know that I talk about this in 1410, some of the students get it. And I imagine it's talked about in 2420 and more of the students get it. And I'm talking about it again here, and hopefully everyone will get it. Nothing will help you more going forward than understanding what's going on at runtime. You go take a class in systems. You take 4400 or operating systems or networks. It really helps to know what's going on in memory when a program runs. So what happens is, memory is divided into really three regions. There's one region of memory that holds the code. And that region of memory never changes. It's read-only. I mean, it's not necessarily read-only memory, but the program doesn't modify itself as it runs. The rest of the memory, there is a stack, and then there is a heap. So who could tell me, what is the stack? What's the purpose of the runtime stack? How is it used when the program runs? Go ahead.
So the frame pointer can adjust with respect to what's needed.
Okay, so we said the frame pointer can adjust with respect to what is needed. So we used the word frame. So this, for example, is a stack frame. And what is contained in a stack frame?
Trace of method calls?
Well, you said trace of method calls, but that's true in a larger sense. But what's in a frame? Yeah.
Doesn't it contain all your local variables, everything that's being used
Exactly.
locally?
A stack frame contains all the variables being used by a particular method call. So it will contain one entry for each local variable and each parameter of a method. So right now we're executing that method G, let's assume. So this is G's stack frame. G needs to keep track, there are no parameters to G, but G has to keep track of the value of X and the value of Y. So when G is called, stack frame is pushed, leaving room to store X and Y. So as we execute along, A gets set to 30. So what that does is it comes over here and, X gets set to 25. It comes along and sets X to 25. It creates a new object and stores this reference to it next to Y. So this is just a data structure. This frame is a data structure that G uses to store its variables. Obviously, it's got to store them somewhere. If that's what a stack frame is, what's a stack? Yeah?
Isn't it like a bunch of references?
Well, it's a bunch of
Stack frame.
frames. So right now there's one stack frame. The running method is always looking, this is right now the top, imagine the stack going in that direction. This is the top frame on the stack. So as G is running, it's always looking at this top stack frame because that's the one that contains its information. Now when G calls F, what's going to happen? It's going to push a stack frame for F. And now the new top stack frame will be that one. When F runs, it'll be looking over here at its frame. What happens when it returns? It's popped. And now G starts running again. And lo and behold, G's frame is at the top of the stack again. So the method always just looks at the top of the stack to find its variables. The frame at the top of the stack contains its variables. So if G called F, which called H, we'd have three stack frames. And gradually they get popped and pushed as we make method calls in return. So that's what the stack is. It's a place to store variable values. What's the heap? Yeah?
A declared area inside of some sort of an external memory.
Okay, so it's memory that's outside of the stack. What's it used for? Right, that's where objects are stored. So when you say, create me a new thing, where thing is there's some constructor for it, it's created on the heap. So in Java, when you say new anything, you see new, that means something's being created on the heap. C# is a little bit different. We'll see that new sometimes can create things on the stack, but not this week. So for the time being, in C#, new is going to create something on the heap. Maybe it's a array list. Maybe it's an array. Maybe it's a window in the graphical user interface. Who knows? But new creates it on the heap. And when you say y gets the value of new thing is created on the heap, and a reference is stored on the stack. So we have 25 is the value of x. The reference to the object over there is the value of y. So let's simulate what happens when the method called f gets xy is made. What's going to change about my picture? What happens when you call a new method? Okay. A stack frame is pushed for it to store its variables. What variables does f have? A and t, no locals. And the parameter variables, a and t, are initialized. Where are they initialized to? Okay. In this case, this is called by value, so that parameter is evaluated, and that becomes the value of a. This parameter is evaluated, y, and it becomes the value of t. So what's the value of x right now? 25, and what's the value of y? This reference. And so when we call the method, a stack frame is pushed for f to use, and its parameter values are initialized. So essentially, with call by value, you can think of it this way. The bits stored right there for 25 are copied up. The bits stored right here, which is a reference to memory, is copied up to there. So with call by value, you are copying the value of the variable. Now, you got to be careful. The object's not being copied. What's being copied? The reference. Whatever is stored here. The value of the expression. So some people want to call this call by reference. No, we're passing references, but it's not call by reference. Call by reference is a different thing. But y and t both refer to the same object. So now we just start executing. What happens when we say a gets 30? Right, code has been generated for that method that comes over to the stack frame, finds where a is stored, and changes it to a 30. Okay? This is just the data structure that's used by the running program to keep track of things. So that changes to 30. Then we call a method on this object, t.change. Now, that would result in another stack frame, which I'm not going to show here. But it's going to change something about this object, right? It's going to modify in some way. So I'm going to animate that by just saying, okay, it becomes yellow. Maybe what change does is it makes the object yellow or whatever. So now we have a yellow object before we did. And then the method returns. So what happens when the method returns? The stack frame is popped, and we pick up where we left off in G. So we just executed this thing, so we go on with whatever comes next, which isn't anything. And our picture is now that. So from the point of view of from the point of view of G, did X change? No. Did Y change? It's the same reference, so Y didn't really change, but the thing it refers to changed. The object became yellow. But these two things contain the same thing they did before. 25 in binary, and whatever address was stored there is stored there still. But it refers to a modified object. So that's what's happening when you get method calls. That's what happens behind the scenes. in memory. And you've all written programs probably that suffer stack overflow. When do you get stack overflow? Stack exhausted, whatever it's called. Well, infinite loop doesn't necessarily cause a stack overflow. Yeah?
There's an allocated amount of space per language, and once you surpass that language, then you get a
Okay, so there's some limit to how big a stack you get. And if you keep pushing frame, pushing frame, pushing frame, pushing frame, eventually you'll fill this, there'll be no space left. And that's when you get that stack overflow exception. But what would cause that? What could cause sort of an unbounded number of frames to be pushed on a stack?
Recursive function?
Yeah. Infinite recursion does that. So if the recursion goes too deep, you end up with too many stack frames. And you blow the stack. A loop isn't pushing necessarily, just sitting in a tight loop doing some arithmetic isn't going to do anything to the stack. It's not pushing stack frames, it's just using time. All right, so that's call by value. And next we'll look at, well, we're going to look at something different, I guess. Let's see what I'm doing here. Did I just change anything? Oh, okay. Oh, okay. All right, now I realize what my slide is showing. So I changed the program slightly. Look up there at F, and you see before we were calling a method on T that changed the actual object. Now I'm not modifying the existing object. I'm creating a yet another thing object and storing it into the variable T. So let's see how that works with call by value. What will happen? So right now we got initialized like before. What happens when I make the method call? What's going to be in the stack frame? It'll look like just like before. The 25 is copied up, the reference is copied up. Now A gets changed to 30. What's going to happen? That turns to 30. And then we set T to be a new thing. So now we're going to store a different reference here. It'll refer to the heap, to a different thing object. Maybe this time it's a triangle. So we've changed what's stored there because we did an assignment to a variable. Now, what's going to happen when we return? Wipes out the stack frame. That becomes garbage. The triangle becomes garbage. And this looks exactly the same. Same 25, same reference. And the object hasn't been changed because the object wasn't changed. A new object was created and stored somewhere else. So basically, calling that method had no effect as far as G is concerned, except there's some garbage on the heap. Eventually be garbage collected. That's call by value. Yeah?
In terms of computer memory hierarchy, where would the stack be stored when you're running a program?
Well, he's asking, where would the stack be stored when you're running a program? So when you're running a program, that's a process. The operating system gives you some memory for your process. And you can use that memory how you like. A common strategy is to allocate the stack. Imagine it's just, you've got this long chunk of memory. Have the stack on this end growing in this direction. Have the heap on this end growing in this direction. And one idea is just to let them grow until they collide. Now at that point, you really don't have to say you're out of room. What could you do when the stack collides with the heap? How could you make more space? Yeah?
You just ask the operating system for more memory?
Well, yeah, I suppose you could ask for more memory, but I suppose that's not going to happen. I suppose you've got all the memory you're going to get.
Starts overriding?
Well, you can't. You don't overwrite. If you were programming in C or C# or C++ rather, yeah, you'd probably just start overriding and cause some kind of mysterious failure. Yeah.
Maybe you could start compressing it.
Right. That's you compress the heap. Typically, the heap is going to have holes in it, memory, places where objects were created and then garbage collected. And that's going to leave sort of a Swiss cheese effect in your heap. So at some point, when you garbage collect, you also compact it. You rearrange all the objects so they're compact, so you got the space. But you can run out of space when if the If the stack grows all the way to the heap and there's no way to recompact the heap again in your memory, then you're either out of heap or you're out of stack. I'm not sure how C# works, but in Java, when you run a Java program, there's just a maximum stack size. And you can change it. There's a command line option when you run Java. You can say how big you can allow the stack to get, but there's just some fixed size a stack can be, and then it can't become any larger. Now, when you do multi-threading, and you have more than one thing going on at a time, that just means you have multiple stacks, one for each thread. That's a topic for another day. Any other questions? Okay, now let's do the same. We're going to go through the same two examples using call by reference. So we got the same setup. We're calling f, and we're going to assume now they're, say, ref parameters. I guess I should have said ref up there, but anyway. What happens with call by reference? Clearly, we're going to get A and T up here in the stack frame for f. What will be the value of A and what will be the value of T? What needs to be stored in A and T? A reference. So actually, you get some picture like this. A contains a reference down here to X. And T contains a reference down here to Y. So anytime F wants to store into A, what it's going to do is say, I want to store here, but I'm just going to follow the reference and store down here. And the same thing for T. T, it'll come down here. So what's going to happen when we say A gets 30 up there? It's not going to come over here and store 30 here. What's it going to do? It's going to store 30 here. So it's going to follow the reference down into another place and store the 30 there. Now, does this reference necessarily go to another place on the stack? Could this black dotted line go out into the heap somewhere? Okay, how could that happen?
Property of an object.
Yeah.
Well, could you pass like a new object to it that doesn't have a different, like?
No, you have to, it has to do with the object though. Yeah?
So if the object has like properties like
Sure.
you've defined to it, like you can make
Suppose this object here has a property, a public property P. Then we could have, let's say it's an int. We could have passed, instead of passing x as a parameter, imagine passing y dot p. That would be some memory location in the object, in which case this reference from A would point over to that memory location in the object. So with call by reference, you just got to make sure you're passing some place that can be assigned to, some place that can be changed by assignment. So it can be a property or an instance variable in an object. It can be an array location, because arrays are stored on the heap. It can be a local variable or parameter. What's going to happen when we do t.change now? When we make our object yellow. Same thing as before, but how will it find the object? That's the only thing that's different, is what actually happens.
P to Y to the object.
It's going to follow this reference down here and say, oh, there's the reference I need, and change that to yellow. So the same result, it just takes an extra hop. So you can see that if you need the value of a reference parameter, it's less efficient than a value parameter, because you've got to do an extra step to get to it. And then what happens when it returns? What happens when f returns? We see that's the same picture we got before. So you can't tell the difference between call by value and call by reference with this setup.
This one, change the X.
Oh, you're right. You can't tell the difference with this, but you can. You're right. It's not the same as before. This was 25, now that's 30. Okay, now we're going to change f there, create a new thing. We make the call. It looks like that. What happens when we say A gets 30? It's changed here. What happens when we say T gets new thing? It's going to create the new thing object, and instead of storing it here, it's going to store it here. So it stored the reference to the object, not here, because this was a reference parameter. It stores it to the thing in the thing it refers to. And then when it returns, we got a different picture. So that's different from the original one as well. Both of these variables were modified because they were passed by reference. Yeah?
Why doesn't X point to somewhere on memory that stores 30?
Okay. He's asking why does X not point to some place in memory, an object that contains 30? The answer in Java would be that primitive values are always stored directly on the stack. They're not objects. And things that aren't objects, primitive values are stored directly on the stack. So true, false, 30, characters, things like that are stored on the stack. Objects are stored on the heap. In C#, what we'll see is that when you declare, you can create new types of data. Some types of data, when you create them, they're stored on the heap. Other types of data, when you create them, they're stored on the stack. And ints happen to be a kind of data that's stored on the stack. Now, what would be the cost of storing this int out on the heap? An object that contained the 30 with a reference to it. Why not just be uniform, store everything the same way? Yeah?
Slower?
It's just slower, right. If you want to do something to 30, you'd have to follow a reference and get the 30. There's no advantage to storing it indirectly. There's advantage to storing objects indirectly because they're big, they take up a lot of space in the stack. If you copy them, they take up a lot of space. And, but not for ints. For small primitives, it's not an advantage. Yeah?
So when we call a method like the try parse that was in the last example, even though int is a primitive, because it has that method, does the compiler just know that there's a certain set of methods? Does that make sense? Because if there's not a reference to an object, how does it know that there's a method associated?
Well, what's being passed is the compiler knows that A is a reference to an int. And the compiler knows what you can do with ints. You can add them, subtract them, multiply them, divide them, just by virtue of there being ints.
I was talking about in the last reference when you did the int.tryParse method, where it was like an object method. Because that is stored on the stack, how does it know that it has that object method? Is that just something that's...
Okay, so I said everything has two names. So primitives have two names. So the primitive type int in C# corresponds to something that's similar to a class called int32.
Oh, that's right, because it wasn't a value, it was a...
Right, and in C#, we'll clear this all up next week, but in C# you can have values with new types, with methods, constructors, and all that, except that when you create a new one of those, it goes directly in place. It doesn't get stored indirectly on the heap. And ints are such a thing. But for right now, we won't worry about that distinction. So this is call by reference versus call by value. Yeah?
When you say primitive types on the stack, because the memory size required for primitive type is kind of the same as memory required to store the address.
Okay, so he's observing that the space it takes to store an int is the same it takes to store a reference to something. On a 64-bit computer, it'd be 64 bits. And that's why it's a lot less, rather, if every int had to be referred by a reference, you're doubling the amount of space it takes to store your ints. You've made all your int arrays twice as big, all your double arrays twice as big. And every time you want to get one, it takes twice as long. So it's just an engineering decision. Sometimes it's better to store things on the stack. Sometimes it's better to store things on the heap. C# lets you choose when you define a new type of data, whether it's going to be the kind of thing that's stored in place or the kind of thing that's stored indirectly. Java doesn't give you the ability to make that choice. Yeah?
Is there a different name for reference stacks? On the stack for the heap as opposed to other references on the same stack?
Okay, so what he is observing is this is a reference, one kind of reference, and this is another kind of reference. This one is, I drew in white, I drew this one in dotted black. And and he's asking, is there a name, and not one that I know. It's confusing. They serve different purposes, but they're both called references. But when we talk about call by reference, That refers to these kind of dotted references. You're passing these kind of references as parameters. Yeah?
Do we know if there's like safeguards in place to prevent something like a buffer overflow with the stacks, like overwriting part of the stack below it? Is there something like that in C# so that can't happen?
Yeah, in C# you don't have to worry about the stack being overwritten because you can never get a reference like this back into the stack. In C and C++, that is a possibility that you write past the end of an array, and what you're actually doing is writing somewhere in the stack and changing a variable. Or you're writing into the code and changing the code. Or if you're lucky, you're trying to write in memory that doesn't belong to your process and the program crashes. Now, why do I call that lucky?
You have to rewrite the code.
What's the advantage? Yeah.
It's noticeable.
It's noticeable. What's bad in C and C++ is you do something that's wrong and it doesn't crash right away. It crashes later because of what you did. It makes it really hard to debug. If you know that this here memory location caused the program, now, writing a memory location caused the program to crash, you can debug it. If what caused it to crash was 5 minutes ago it wrote to a bad memory location and you weren't told about it, tough. Hard to debug. Any other questions about this? Yeah?
How would you tell C# if you want to use call by value or by reference?
Okay. He's asking, how do you tell C# which you want to use? What's the answer to that? Okay? So here I'm defining a method, I'm defining solve quadratic. How am I telling C# whether to use call by value or call by reference here?
Out.
Okay, the ones that are labeled out, is call by reference. The ones that aren't labeled are call by value. And that's it. And you have two options, out and ref, both denote call by reference, but they differ in whether or not the method we're calling can use the incoming value of the variable. Any other questions? All right, we'll take a quick break and look at something different. Again. Okay, so for this assignment, you're implementing a formula class. So a formula produces objects that represent formulas you might see in a spreadsheet, a simple spreadsheet. So you're implementing a formula class, which means you're going to need to figure out how to represent a formula, because there's a constructor that creates a formula, and there's an evaluate method that evaluates formulas. And there'll need to be instance variables that store information so that the class works. And I all the time see mistakes. Students make the same mistakes over and over again with instance variables. And I just want to tell you about them so you don't make those mistakes. Now, when I say instance variable, do you know what I mean? Maybe you've heard it called member variable. What's an instance variable? Yeah?
It's a variable on the object.
Okay, it's right. So it's in terms of a class. Where would you find the instance variables of a class? Well, initialized by the constructor. Where would you find out? If I asked you, gave you a class and said, what are the instance variables? How would you decide? Well, they may be declared at the top. So they're variables declared inside the class, not inside of a method, but inside the class, top level of the class, and they don't say static. They're not static, they're non-static. Now, when you declare instance variables, what's the importance? What happens when you declare? Let's say you have 3 instance variables and you declare them. What does that mean for the objects that are ultimately created?
You can reference them with dot operators.
Okay, it can access them with dot operators, sure, but yeah.
Each time a new object's created, it's like a new variable is created.
Right. When you create an object, those 3 variables are what are stored inside the object. So that's why I call them instance variables. Those variables, there's a new set of those variables created for each object. Object just encloses the instance variables. So it's not like when you declare an instance variable, there's one for the class, and that's all. In fact, when you declare them, there are none. You can't use them until you create an object, and then the object contains them. So that's what instance variables are. So one thing I find, let's also say about static variables. What happens if you put the keyword static? Instead of saying int size, private int size, you say private static int size.
There's only one pointer to it.
Right, in that case, when you declare something static, there is only one variable for the class. And it's shared by all the objects. So each object does not get its own static variable. Static variables associated with the class. Instance variables go with the objects. So, I see students that will declare, they got a method that needs some local variables. Like, they need a local variable I, because they got a loop inside their method. So rather than declaring it locally inside the method, they just create a variable and they say static I, private static I. Why is that bad? Yeah?
Because if it's nothing more than just used in some sort of iteration, a for loop or something, you're basically creating this variable that's taking up storage space that is really insignificant in its value other than that one time in the loop that can be easily...
Right, so by declaring it static, you've made a variable I that can be referenced by any method in the class. So if you have this idea in 2 places, you say, oh, here, I need a variable I here, I'll declare it static, because I like to see all my variables at the top. Or maybe someone once told you, all your variables ought to be in a block at the top. Okay? So you declare I, rather locally, you declare it static at the top, and then you write another method and say, oh, I need a variable I. Oh, there's already one declared, I'll use it. Now you have 2 methods, both using a variable I, and it's the same variable. What could go wrong? What happens if this method is iterating and it calls this method, which then starts iterating using I? They're both modifying the same variable at the same time. Local variables are a big advantage. You don't have to worry about your local variables being corrupted by some other method. So make your local variables local. Okay, this very assignment, you'll see the need for helper methods for it. And you'll have the choice. You've got to get information from this method to this method. Everything's static. All the methods are static. How do you get information from this static method to this static method, this static helper method over here? Yeah?
Use a parameter.
You pass parameters. I see students all the time, for some reason they don't want to declare parameters over here, so they just make a static variable, or a couple static variables, and pass the parameters via the static variables. Again, bad idea, that's not what they're for. In fact, I would go so far as to say, don't use static variables at all, unless you really know what you're doing. Certainly don't use them to replace local variables and parameters. Now, one place where statics are useful is when you need constants. You've got to declare some constants. Like, rather, you shouldn't use magic numbers in your code. So if you need a 5 for some reason for an algorithm, and someone looks at your code, they see a 5 in it, where did that 5 come from? It's better to declare a constant that explains what 5 is, and then use the symbolic constant. That's a good use for statics, but they aren't variables anymore when they're constants. So in C#, you would declare a const, and now it's a static constant, and it can't change out from under you, and it provides good documentation. So that's static constants are fine. I forget which was the first slide here, but I'm obviously working on that. Okay? And like I said, the use case for a static variable is if you really need, suppose you wanted to write code, you want to know how many objects have been constructed. So you start your program, you got some class, there's a constructor for it, and you want to know how many times the constructor has been called. Why would you have to use a static variable for that, to hold the number of times the constructor has been called? Yeah?
So the variable doesn't change every time you create a new object.
Right, well, yeah, so if it weren't static, each object would have one of these variables, and it'd be set to 1 when that object was created, and then every object would have a count of 1. So if you need to have something like that, some class-wide variable that holds something like the number of times the object has been called, or some resource that needs to be shared among all the methods. That's when you use a static variable, not for these other purposes. And that's why I say, unless you really know what you're doing, do not use non-constant static variables. They're just bad. Okay, back to other mistakes. What would happen if you declare an instance variable static? So you're implementing a set. And for the set you need, let's say you want an array and a size, 2 instance variables, an array and a size. What happens if you make those 2 variables static? Yeah?
Well, every iteration of that object now just refers to that one
Right.
variable.
Now every object, instead of every object having their own array and their own size variable, now they all share the same one. That's not going to work. You effectively only have one object, because they're all sharing the same representation. So you don't declare instance variables static. That'll only work if you can only have one instance. So I usually, in fact I always include tests like this when I grade. I make sure that I can create, say, 2 formulas that are independent of each other. That if I have this formula and this formula, they're not the same object. Okay. Some students want to declare local variables as instance variables. So they have a local variable again, like I, and they declare it as an instance variable. Why is that even worse than declaring it as a static variable? What happens when you declare just some random variable as an instance variable when it doesn't need to be? When does a variable need to be an instance variable? Yeah?
You can access it in multiple methods.
Right, if it needs to be accessed in multiple methods. So in the case of the set class, the array and the size need to be, you need to have access to those variables when you are doing an insert into the set, or a deletion from the set, or getting the size of the set, or printing the set, or whatever. That's part of the representation. But some local variable, say the integer that the variable you use for iterating, I, what happens if you make it an instance variable? Besides the mistake that we talked about before, that now multiple methods are going to be clobbering the same I. Yeah?
A lot of wasted space.
A lot of wasted space. Now, every single object, suppose you create 1 million objects. Each of them is going to be storing I, where it doesn't need to. It's a waste of space. Instance variables should always be private. They shouldn't be public or protected. Reasons we talked about last time. It's also important to document your instance variables. Document them because they're the key part of your implementation of a class. And they need to be documented. How do they interrelate? What do they contain? What does this array have to do with representing a set? So keep that in mind as you're working. Yeah.
If you're not supposed to have public or protected instance variables, like where else are they used and why even have those options available?
Okay, fair question. Why is it even an option? If I say that instance variables should always be private, why do they let you make them public or protected? Yeah?
Could it be for debugging, testing?
He's saying maybe it's for debugging. Yeah?
Just because it's generally good practice to never have them public, doesn't mean that there isn't an instance when it should be used like that.
Okay.
I don't know.
So he's saying, there's always exceptions. Yeah?
In 2420, we had all these node classes where all the different nodes had instance variables of different nodes stored inside the class. So the value they were not initialized.
Mm-hmm.
And so then you would always be initializing those, and you were directly calling them. It was actually really necessary.
So in C#, those would be properties. And maybe to answer the question, the reason is because I didn't design the programming languages. Right? If I designed Java, I may well have said variables must be private. Not everyone agrees with me. So, especially the bit about variables never being protected, always private. So, I teach the class, so I get to teach you my opinion, but, my opinion is not a whim. It's well considered, years of thinking about it. Any other questions? Now, for the current assignment, the class you're implementing is just, well, I'll take it back. It is a class, it's not statics. There are formula objects, so never mind. Okay, now, we want to talk about testing. You're going to be doing a lot of testing this semester. I gave you just a few unit tests for your formula class, but if that's all the tests you use on your class, you're probably not going to get a very good grade. You need to, write your own test. And we're not grading your test this time directly, but other times we will. So let's talk about testing. So here are some reasons that you might ask the question, why must we test software? Okay? And these are possible answers. We test software because we're not good enough programmers. So we have to test. We don't get it right the first time. We can't keep from making mistakes. We're forced to test because we don't design properly. We can't understand what a client says. We are failures. So those are all reasons you might pose for why we must test software, but it's none of those. Why must we test software? What would be a better way to do things?
Get it right the first time.
What's that?
Get it right the first time.
Get it right the first time? But how would you know that?
Be a robot. Be a computer.
Yeah?
Basically, the reason why we test is because we want it to work.
Okay. We need to get confidence. We need some confidence that it works, yeah?
That's exactly what I was going to say, because then we can demonstrate the code does exactly what we
Okay.
say it does in small, understandable chunks.
So in a better world, we wouldn't test. We would do mathematical proofs that our program is correct. In a better world, we would state, using mathematical notation, we would say precisely what it is the program is supposed to do. And then we would have a system that would prove the program does that. And there are researchers working toward that sort of thing. those techniques are used more often in hardware to prove that chips are correct than in software. But those techniques are used in small mission-critical pieces of software. But they don't exist at the moment. So the reason we test software is not to prove that it's correct. It's to find problems. So when you write testing code, that needs to be your point of view. You need to say, I am trying to find defects. I'm trying to find mistakes. It's no big deal to write a test case that your code passes. What does it tell you if your code passes all your test cases? Does it mean your program is correct? No. Now, what does it mean if your program fails a test case? You know that it's wrong. You know something if it fails a test case. You don't know anything for sure if it passes test cases. So the goal of testing software is to find problems. And you want to find them as soon as possible. Because the longer you wait to find a problem, the more expensive it is to fix it. Yeah?
What if the program is right, but your test is wrong?
Okay, so fair enough question. You said, what if your test is wrong, your program is right? So I will have to revise my statement. If your program fails a correct test case, then you know the program is wrong. Okay, so testing is the process of executing a program with the intent of finding an error. And so a good test case is one that has a high probability of finding an error. And you've got limited time, so if you're good at testing, that just means you're good at finding mistakes in programs with a minimum amount of effort. Now, we can gain confidence in our program if we pass tests, but it doesn't mean that. You can never prove that it's correct. You can only show that it's incorrect. And I don't know where the statistic came from, I don't remember anymore, but testing can take a lot of time. And I want you to think about your own feelings. Suppose I give you a complicated assignment to do and I don't give you any test cases. How does that feel compared to I give you a complicated assignment to do and I give you a comprehensive set of test cases? You have a very different mindset when you're going in backed up with test cases. What does that say? If you feel good when someone gives you the test cases before you start coding, and you feel bad when they don't, what should you do? If you want to feel good, write your own test cases first. Then you have test cases going in. Okay, so two kinds of testing that we're going to talk about here, black box and white box. So black box testing. The idea behind black box testing is you are writing tests without taking into consideration the implementation. So black box tests, when I give you tests for the formula class, they are necessarily black box tests. I don't know anything about what your implementation is going to look like. I've got the interface is specified. I know what the class is called and the methods are called and what they're supposed to do. But I don't know how you're going to do it. That's a black box test. If you write tests before you start thinking about how you're going to write your code, that's a black box test. The nice thing about black box tests is they're portable. I would not want to grade, part of your grade is based on tests, the result of testing your code. But fortunately, I don't have to write separate tests for each of you. I can use the same set of tests because they're black box tests. So essentially, you've got something you're testing, all you know is its interface and its specification, and you test it to see if it behaves the way it's supposed to, based entirely on the specification. Those are black box tests. White box tests, you take the code into consideration. You design the test with the knowledge of what the code is. Now, what could you do? So with white box, you know everything that you knew for black box tests, but you're also going to take the code into consideration. So what could you do with white box testing that you couldn't do in black box testing? Yeah?
So in black box, you talked about single modules. So maybe in white box, you could test combining those.
Well, with both black box and white box, we're talking about single modules, unit testing. It's not that. Yeah?
I think the code you wrote there kind of suggests something, which is you can Blackbox test both for both if and else.
Right. So you might look at the white box test and say, I mean, you're writing white box tests. You look at the code and you say, well, there's 2 branches. I better make sure that I write a test that exercises both branches. Okay? So ideally what you would do is test every possible path through the code. That can grow exponentially. If you think about loops and conditionals and nesting them, they're just going to be, there could be millions or billions or trillions of paths through the code. But at a minimum, you'd like to be able to at least make sure every line of code is executed at some point in your testing. And you can consider doing that in white box testing. You can take the code into consideration. Yeah?
Couldn't that, I mean, you don't need to write one unit test that will test everything. You can write a bunch of multiple.
Collection of unit tests. Yeah. So let's drop out of these here for a second and actually look at testing in Visual Studio. So over here I've got in the example repository, I have unit test example, so I'll open that up. And let's look at findtest.cs. So I have a binary search method in another class, and I wanted to write tests for it. So this is very simple test for a binary search. So just so you see, the lab's about this tomorrow, but basically you create a unit test project. It's another kind of assembly you can create. The class has to be annotated that way to say it's a test class. And then the actual tests have to be annotated that way. So you've done this sort of thing in Java before. It's very similar to JUnit in Java. I create this constructor here to create a numbers array because the constructor is called before each test. So that creates the array for me to search. So I've got 1, 3, 5, 7, and 9 in it. And what am I doing here? This test present test. How does it work? That test at the top. What kind of test is it doing? So find is the binary search method I'm testing. Yeah?
Check to see if 0 is equal to the result returned by the search.
Okay. So I'm searching my numbers array, which I constructed in the constructor, and I'm looking for 1, and it's supposed to return the index where the 1 is stored if it's in there. And that happens to be the first element in the array. So I'm just asserting that that's the first place. 0 is the first, the index of 1 is 0. So I get 0 back. Okay? What's happening in the next test right here?
Returning -1 for...
Okay? So if we don't find, the 0 is not in the array, if we don't find it, what it's supposed to return is a negative number. Furthermore, it's supposed to be, if you take this number and add 1 and negate it, you should get the index where this element should be stored if it were to be inserted into the array, where it should go. So this is telling you that 0 ought to go at the beginning of the array. So we're telling 2 things. It's not there, and also the answer tells us where it should go. So these are simple tests. And I find students are pretty good at writing simple tests. Where students fall down is writing more comprehensive tests. Say, tests that have, even a test that has a loop in it. So here I've written a loop where I'm doing the assertion inside a loop. I'm looping through the array, I'm looking up each number in turn and making sure it's reported to be in the correct location. So just doing that small change to your test writing habits of using the full power of the programming language to write comprehensive tests that loop through data structures, that do a ton of assertions, can really make a difference in the number of bugs you find. So what do you think of my tests here? Is this adequate? Would you be happy to have your code graded by these tests? Can you see ways to improve it? How can you even answer those questions? Yeah?
Well, in this example, are we testing like edge parameters or anything, or non-valid inputs or anything like that?
Okay. So, yeah, well, all I'm going to assume, I'm testing the specification. And so I'm going to, that requires that numbers is an array of ints, possibly empty, and item has to be an int. So, I'm not going to test what happens if I pass a double, because that can't happen. Yeah?
Duplicate numbers.
Okay. So one thing we assume is the array is in ascending order, or non-descending, it is in non-descending order, so there could be duplicates. So the test I have doesn't test what happens when there's a duplicate. In fact, it's not clear what the specification says should happen when there's a duplicate.
Better understanding of like the specifications of the assignment provide for better tests.
Okay. So actually contemplating writing that test makes me realize there may be a problem with the specification of the problem. I don't remember what it says. Let's see what fine says here. It doesn't explicitly say there's no duplicates, but it says it is arranged into ascending order. So we'll just say there can't be duplicates. Okay? Can you think of any tests to add? How do you know what's a good test? What if we not test systematically? Yeah?
We've always tested success cases, but we've never tested, I don't know if it applied here, but we've never tested like failure cases.
Yeah, well, what we didn't do much testing, at least here, in this place, we looked up every number in our array to see if we got the right thing back. But only one place did we test what happens when a number is not there. So maybe what we should do is look up 0 and 2 and 4 and 6 and 8 and 10 as well. Because they ought to return different negative numbers. 0 should return -1. We look up 2, we should get back like -3. 4 should return -5. So we ought to do that. You might ask yourself, why this array? Why use an array that's just, 5 elements long? Maybe we should create one that's 10,000 elements long. It's easy to do with a loop. Maybe we should create one that's empty, or one that contains a single element. Is that what you're going to say?
Yeah.
So, if you're doing black box testing, you need to focus on the specification and think about the edge cases in the specification. What should it do if the array is empty? What should it do if the array contains one element? What should it do if the element isn't in the array? And then with white box testing, you should be thinking, I've got to at least make sure that every line of code in the method is executed. But how do you do that? How do you make sure that every line of code is at least being tested once? Yep.
We usually test for other methods.
Test for what?
For other methods, except besides.
Well, we're testing, the only method here is fine, so we are testing all the methods. But what C# has, what Visual Studio has rather, is an option under test up here. I can go to Analyze Code Coverage, All Tests. So I'm going to run the tests that way. And you can see it's chugging along up here, and it'll probably tell us we passed all the tests in a minute. But what it does is an analysis, as it's doing the test, it keeps track of what lines of code we're executing. And if we open this up down here, we can, let's say we look at binarysearch.exe. You can see that only 48% of the code in binary search was not tested. And there's a thing I can click on here that'll color the code. So I just clicked on it, so let's go look at, here's my binary search class. And you can see, I hope you can see, oh, you can't. Dang it. So all the code in this class right here is highlighted in light blue. So that means it was tested, it was executed. And if we go up here, you can see that. That's highlighted in light red. That means that code was not executed by the test methods. So So basically what happened with our test class? We didn't test the main, which actually wasn't our goal. Now, let's see what happens analyze code coverage. I want to just do some of the tests. I don't know how to do that. Okay, let's do it this way. Suppose I go to find test right here, and I just do the first test. So I'm going to comment that out. I'm going to comment that out. So all I have is this single test that checks whether 0 is in there. Let's see how well that does. So I'm going to go to test. I'm going to go to analyze code coverage. I'm going to say all tests. And then I'm going to click on show code coverage. And we'll go to search.cs. So it didn't touch the main again. And you can see that because we only did that one test, it happened to not ever hit these highlighted places. So that shows you that just that single test by itself did not exercise all the code. And I want to emphasize that it's certainly good to execute all the code. It's not an end-all. It doesn't mean your program is correct just because you've executed every line of code. I would like to execute every line of code in every order possible, but that's combinatorially impossible. But it's at least a good goal to try to get 100% code coverage. Sometimes even that's hard. And so typically on upcoming assignments, I will say to you, create your own unit tests, and part of the grade is going to be how much code coverage you get. Your goal is to get as close to 100% code coverage as you can. And it's actually kind of fun to devise tests to cover those last bits of code. Let me show you another thing in Visual Studio. Up here on test, I can go to test settings, or not test settings, live unit testing, and start. What do you suppose live unit testing does?
Test it live.
It runs the unit tests as you change it. Okay? So let's go to my code here now. Search.cs. And let me change this. Actually, I'm going to have to make my test more robust if I'm going to find errors. So let me go back and do that. We'll go to search here. And let me just change this index to 1. Okay? And right away it's telling you that you can see it failed some tests over here. And this X here says covered by 3 tests, covered by 3 tests. So you can see as you're coding that you made a mistake that made you fail test cases. And if you correct your bug, then it goes back to correct. So in theory, if you had your unit test all written at the beginning, you could turn on live unit testing and you could watch as your code slowly passed all the tests. Yeah?
For live unit tests, like how much, I guess, like resources does it take to keep that on for the entirety of the coding?
Yeah, I'm not sure how I've never programmed for long with it on. Let's see what the options are here. It says pause live unit testing when battery is below 30%. So I think that's a problem. You can set the timeout, logging. You can cap the memory it uses. You'd have to use it to find out exactly how resource intensive it is.
Could you run live unit testing on just one test? So like if you really can't figure out why you have an index out of bounds, you can just keep.
Yeah, I don't see any way to configure that, but I suppose you could go comment out the other tests like I did. So Visual Studio has these neat tools. The code coverage helps with white box testing. So the way to write the tests is to write them as black box tests. You're writing against the specification. And then see what kind of code coverage you got. Inevitably, you don't cover all the code, and you devise other tests that do that. Now, let's go make a more comprehensive test of fine test here. Let me turn off live unit testing for now. So I sometimes call these stress tests. I want to write a stress test for sort of a better version of all tests. How can I really stick it to my code? How can I give it large amounts of data? Because this will also show up stuff about performance. If your tests take a really long time to run,
Just fill it with random variables.
well, I could create an array that contained a bunch of random numbers, but that kind of randomness makes it kind of hard to. Yeah? Okay, I could write a loop, so let's do that. Let's see, is this thing sorts arrays, right? All right, so let's do this. I'm going to create a list of ints. Let's store let's put the numbers all the odd numbers from 1 to 10,000 in the array, in the list. Okay? So I can create an array as big as I want. 10,000, 100,000, whatever.
Plus equals 2.
All right. That would be good. Plus equals 2. Now what? How do I actually do a test? Yeah?
You just basically run that loop again, and
Okay.
then put the, I don't know, the assert equals true, I guess. I'm trying to think of, what are we testing again?
We're going to test lookup. So let's say int okay, so we turn it to an array. Then we're going to do an assertion. We're going to look up each odd number and make sure that it works. So we have to say no, never mind. Okay, so I'm looking up I, and what should its index be? Look up 1, what should I get? Is it I minus 1? But then when I look up 3, what should I get? So it should be I minus 1 divided by 2, I think. So essentially, to do these big tests, you have to have some way of asking the question, and you have to have some way of knowing what the answer is you expect without having to redo the calculation. So let's at least try, let's try running the test cases now. Make sure we're passing that test case at least. Okay, so that's good. How could we improve it to make it even more robust? It has to be an improvement that works like in a minute or two. Yeah?
You can do like the negative test cases at the same time.
Okay, so I want to do a similar one. And I'm going to go from 0, start at 0 instead. And when I do the lookup, what should I expect to get as my answer? This is where it gets a little tricky. So what did I say before? That if you negate the answer, if you add 1, yeah, add 1 and negate, and that gives you the index of where it should go.
So what, you just leave what you had, and then add.
All right, so now I'm kind of stuck right here. I would try to think it out, but I'm out of time. So I'll figure out what that is and put it in, and you can pull it later. But the idea would be to make sure I'm getting the right negative number.